Welcome back to Frontrunner Podcasts. My name is James Bowen, and today we've got Phil Kaya on, and we're going to be talking about quantum computing. Quantum computing is quite an interesting topic. Phil, welcome to the show.
Yeah, thanks. Thanks very much. Pleasure to be here.
You know, Phil, quantum computing, we've been talking about that for the last couple of number of years, decade or so, and there's regularly in the media, there's breakthroughs in terms of the capability of quantum computing. And when I think of quantum computing, I think of the kinds of models that we can tackle now with quantum computing, which weren't necessarily doable with the traditional classical binary computers that we have today. So there is the optimization models. There are models which we have complex variables, and the understanding of how these variables interact are themselves maybe not well understood. So maybe you could speak in terms of the kinds of modeling that we can try and tackle with quantum computers. The modeling usually is around, of course, the data and variable structure themselves. Maybe you could start us off by giving us a bit of a sense for the types of models that we can now tackle with the quantum approach.
Sure. So when you say models, so I think more in terms of computing problems, hard problems that we need to use computers to solve. And as technology has progressed and computing power has gotten more and more, more and more powerful, but the problems that we're trying to address and the amounts of data that we're trying to process to solve these computing problems is growing, at an even faster rate. And so, especially with the advent of machine learning and all of the computing requirements that brings, certainly, we're pushing the limits of what, and beyond of what classical computers can do. When I say classical computers, I mean the computers that we built today, the supercomputers, everything from your desktop, your laptops, to the most powerful Cray supercomputers, that NASA might use. So there are a range of problems that we use computers for, and I mean, you mentioned optimization, which has an incredible number of business applications for logistics, supply chain, scheduling, any of those kinds of things where you're trying to find an optimal way of doing something. And another application area that we're seeing that we're using computers for is simulation of materials and simulation of physical systems to try to, and this is where the word modeling I think is very appropriate. You're trying to use a computer to model how a new material that you're trying to design will behave, or for example how a candidate pharmaceutical might interact with proteins, etc. And so these are really hard computational problems, and what that means is that as the size of the instance of the problem you're trying to tackle grows, the amount of computing resources you need to do that grows, even faster, far faster. And so, you can very quickly run out of available computing resources, both memory and speed, time on the computer to do it. And now quantum computing is, a very it's a fundamentally different way of computing. It's, some people, might think of quantum computing as sort of just classical computers souped up or running faster, and that's actually not the way to think about it. Quantum computing involves a fundamental shift in how we think about computing, how we think about information itself. What data is actually very different for a quantum computer. But quantum computers, I think it's important to understand that quantum computers will not replace classical computers en masse. They won't. There are certain things that classical computers will always be more suited to do, but there are certain hard problems that quantum computers are especially suited to, and some of those we've already mentioned. Often, certain optimization problems, certain types of quantum computers are potentially far more powerful. We say exponentially more powerful than any possible classical computer that we could build. And also for materials science type problems, where we're trying to figure out how material will behave, or model. So some companies have some automotive companies, for example, have been using have been experimenting using quantum computers to try to design better batteries and sort of to simulate the chemistry that goes on in the batteries. And there are companies exploring the use of quantum computers for precision medicine and for drug discovery. And then of course, there are the cybersecurity cryptologic applications of quantum computers, which that's sort of what originally got the world very excited about quantum computers was what it could do in that space. So yeah, does that answer your question?
Absolutely. There's a couple of things there based on what you're saying that I want to pick up on. One is the idea of modeling, and certainly from my perspective, a model is a representation of reality. So we have both the structure as well as the data component to it. But traditionally, in complex spaces, we've had to make a number of assumptions in a model in order to scale it to the point at which we could actually compute the results. So my first question then is around the data side of it, because you had mentioned it when you were talking there that data would be different or treated differently in a quantum space. If we have with classical computers limitations on our modeling representation because of the computational load of representing reality, and perhaps we don't even understand reality to its full extent, we can therefore better represent in a quantum computer, my understanding is, correct me if I'm wrong, because we can expand or better tackle the assumptions. But the point that you mentioned was around the data side. Now, wondering if you could elaborate around how quantum computers might treat data differently.
Right. Okay. So good question. So what I mean when I say that for a quantum computer, we have to rethink the notion of what we mean by information. Perhaps data wasn't really the right word to use there. In a classical computer, what you're operating on are binary digits, bits, and a bit is either 1 or a 0. And your data is encoded in long strings of bits. That's on your hard drive. Your hard drive is really just a big sequence of 1s and 0s. And you encode your data in binary in that way. And then a classical computer operates directly on binary data, on those bits, and it does, fundamentally there are a few basic operations you can do on bits. You can flip them. You can have one of them flip if another one is 1 or a 0. There's some very basic operations you can do on bits. They're called basic logic operations, and computers, classical computers, really are just built on a few basic binary operations, scaled up, tremendously. In a quantum computer, you actually have what's called a quantum bit, which is a generalization of a bit. In a quantum computer, a quantum bit of quantum information, has 2 states, 0 and 1, same as a classical bit, except what's different in a quantum computer is that the state of a quantum bit can actually be in a superposition of the 0 and the 1 at the same time. So it can kind of be floating between different states, and it can actually take on a continuum of possible, values between 0 and 1. And that's one way in which quantum computers are different. So, for a quantum computer to operate and to do its magic and to operate quantumly, it needs to be operating on these quantum bits. But at the end of the day, the information, the data that you have that you want to feed into the computer to solve a problem is going to be just classical data like anything else. Whatever the input to your problem is, and at the end you're going to get an answer out of the quantum computer that's going to again be binary data. It's going to be a string of 1s and 0s. And so what goes into the quantum computer and what comes out of the quantum computer are both classical data. But what has to happen inside the quantum computer is that it has to take that that input data, and it has to represent it in quantum bits. And so that is a sort of a technical challenge of for people building quantum computers. there's a number of things that you have to do to build and implement a quantum computer, and one of them is to take your input and to encode that input into quantum states. You take your strings of ones and zeros, but you make them, you turn that into a string of quantum bits that have those states, and then you allow the quantum computer to explore and operate quantumly on those inputs. Does that make sense?
Absolutely. If we got that data side sorted out, I want to ask you a question around the artificial intelligence side and the quantum side, because you mentioned those two
Sure.
together nicely. And as I mentioned, if we consider a representation of reality, and we have the data component to that, devising that model of reality can sometimes be quite a chore, given the kinds of domain areas or applications you mentioned. With AI, we might have the possibility of using an AI algorithm or approach to help us define what that model is, what the connections are between the data variables. So that seems to me to be quite an area in which we could both define the model and use that model by combining artificial intelligence and quantum. Can you give us a sense for how that might work out in various organizations or industries? I can think, for example, in weather forecasting, being able to define both the state of the weather and therefore its possibilities. Because in weather forecasting, one of the primary issues is understanding the current state, and then how that state will evolve is better known, or at least some of the algorithms are there, but understanding the current state of the weather is the real challenge. So perhaps you can give us a sense for how quantum computing and AI can help change some of the various application areas.
Right. So there's been a lot of talk and excitement around, the possibilities for what some people call quantum machine learning or quantum enhanced machine learning, or trying to figure out, is machine learning or AI one of those places where quantum computers can bring an advantage, can bring a paradigm shift, and the answer is not really very clear yet. The people have looked at various possibilities. At this point, what we do know is that there are certain ways in which quantum computing can enhance particular types of machine learning by solving optimization problems that are part of the whole sort of AI chain, if you will. And so we don't yet know how to do machine learning itself natively on a quantum computer. So that's still, I think, a research area that's being figured out. But what we do know is that for certain types of classical machine learning, there are certain sub problems or certain bottlenecks that you can that require you to solve hard optimization problems, and you can use quantum computers to speed up the solutions to those problems. And so the quantum computers just become part of the tool chain, if you will, for machine learning. But I think it's a very interesting question, but I don't think the jury's still out on how quantum computing and AI or machine learning are really going to come together. One interesting thing you talked about. You talked about models and modeling what's going on in reality or in the physical world, and one of the reasons why quantum computers are so powerful for material science, for example, is that with a quantum computer you can much more easily directly simulate the quantum mechanical effects that are going on in these systems. So one of the things that has always been really hard for classical computers to do is to simulate and model quantum mechanical systems. And the reason for that is that when you try to describe all of the properties of a system, like you're talking about the weather. I mean, the weather is not really a quantum mechanical system, but when you're trying to model the weather, what you're trying to do is basically figure out how different air masses are going to interact and how different temperature gradients are going to behave, and you're trying to model a physical system. And in that case, in the weather system, quantum mechanical effects aren't really relevant to how the system as a whole will behave. But for certain things, and especially now as we're trying to design much more advanced materials, and when people are studying what's going on inside our heads, in the brain, and in certain biological systems, it's now becoming more important to try to understand all of the quantum mechanical effects that are going on between those within those systems. And that is very hard for a classical computer to do, because the amount of information that you need to describe the full quantum mechanical properties of a system is huge. It grows exponentially as you grow the size of your system. So if you have a system that only has a few particles and you're trying to model that, well, you can probably do that in a classical computer by just encoding all of the quantum mechanical properties and running it on your classical computer. But once you get beyond, even probably, it depends on the system, but even beyond maybe a few dozen particles or fundamental units, when you're trying to describe those fully quantum mechanically, you just rapidly run out of available computing power. And so, because a quantum computer is a quantum system, it can very naturally simulate and model, the full quantum properties of a physical system. And that's why, for example, in material science, quantum computers can be so powerful, because they can directly model and explore and simulate the full quantum mechanical properties of the system.
That'd be really interesting, and it suggests a whole number of different applications. You mentioned better understanding of the human brain, but if we look at the material sciences side, that suggests that over the course of once quantum computing becomes more of a reality, that we should expect new kinds of composite materials, perhaps somewhat addressing the environmental issues of our current materials, perhaps developing materials that have properties that will go way beyond what we can imagine.
Absolutely, for 100%. I mean, I think for me personally, that application space for quantum computing is one of the most exciting ones, because it's one of those technologies that will lead to paradigm shifts in all kinds of other technologies, as you're saying. Once we're able to simulate and model physical systems at the quantum level, the range of things that will enable is mind-boggling. As you say, advanced materials that have properties that can be controlled in ways that we can't do today. In pharmaceuticals, I mean, the potential there is incredible. To be able to design drugs, design medications more effectively, to be able to predict. One of the things that some people are using quantum computers to do, or in their research, is in precision medicine, to be able to predict different diseases, to predict when a person is going to have a particular condition. So I think quantum computers, the simulation and material science applications and the pharmaceutical applications for quantum computers are for me the most exciting ones, because what they open up for the future in terms of other technologies that are going to be enabled by that is the sky's the limit.
It is, because both of those, the material sciences and the pharmaceuticals, are really, as you've alluded to several times, are really core to so much of our economy and society. Not only the health and wellness of individuals, but all the ways that we take knowledge and represent it in a tangible form through material sciences. Everything from our vehicles and our airplanes and our products, even things, our kitchen utensils, all of that rests on the material sciences, and the potential may be there to come up with different properties around material sciences that can be perhaps reused or composted better. So I get what you're saying in terms of this pyramid of sort of upside down pyramid of possibilities. Quantum computing is at the base, and then other core elements of our economy are then affected. And I imagine after that, it becomes more difficult to fully understand how that's going to cascade out. If we say we're going to have a big impact on the pharmaceutical industry and the material sciences, from there, it it cascades out into so many different possibilities that I imagine it's hard to predict how that'll end up.
Absolutely. I mean, there's a famous prediction when classical computers were first coming into the fore. There's a famous prediction that I forget the number, but there was a total world market for only a handful of computers, and originally computers were envisioned as being number crunchers that would do some very specific calculations for us, but nobody would have been able to predict the internet, for example, which ultimately was something that was only made possible because we built computers and learned how to network them and all the rest of it. So I think that's look at the classical computer, and nobody could have predicted all of the changes in almost every area of technology that has been enabled by the advent of computing. So quantum computing, I think, is going to be another one of these cases where we have some ideas right now, but we're really at the beginning. We're really at the start line. And we have some ideas, and we're looking around and saying, okay, quantum computing is going to be amazing. It's going to help us with this, 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 and this. But I think if we fast forward 10 or 20 years, and longer, we're going to look back and say, wow, we never would have imagined that quantum computing would have changed, all these other things that it has.
Absolutely. That cascade effect is so difficult to predict. As we come to the end of our Frontrunner podcast, Phil, I'm wondering whether you can give us a few takeaways or things to remember. I think you summarized it quite nicely there, and I appreciate the time that you're spending with us today. But is there a couple of takeaways that our listeners can keep in mind as they read articles about quantum computing and read articles about, the state of the art and the latest breakthroughs that are taking place?
Yeah, that's a good question. So, I think one of the takeaways is that it's coming. It's coming rapidly. When I say, what's coming rapidly, the actual commercial application of quantum computers to solve, meaningful problems. So quantum computing is something we've been hearing about for a couple of decades now, in the news and the media, and but it's always been something that's sort of years in the future. And there was some companies were more forward thinking than others, and some companies did invest in understanding quantum computing and starting research efforts to try to prepare for it. But now it's we're going to very soon, within the next I think within the next year, we're going to start to see commercial applications of certain types of quantum computers to solve real business problems. And so I think companies, problem owners today who aren't making an effort to think about quantum computing and to start to plan for it, to do some analysis around how to leverage it, and they're going to be left behind. So I think the takeaway is that this is no longer something that we're looking 5 or 10 years out. We're going to start to see real applications of quantum computers coming very soon, and I think it's important for people to start to plan for that and to look for how they can capitalize on the opportunities that are going to be provided by that in the near future.
Hey, thank you, Phil, for joining us today on Frontrunner Podcast. Thank you very much.
My pleasure. Enjoyed it. Thank you.